Thank you very much. I told you I'd correct you, and it's $1 billion a month. So I'm Samuel, creator of Pydantic. That's how I'm best known in the Python ecosystem. Founder and CEO of Pydantic Labs, where we do a bunch of different things. Pydantic, the original library, continuing to maintain that. Pydantic AI, our agent framework, which I'll touch on a little bit today. Pydantic Logfire, the observability platform, which I will also touch on a little bit. And then Monty, which is what I'm talking about mostly today. I'm a long-time Python and Rust developer, and now AI talking head like just about everyone else. At least I didn't come from React and become an AI expert overnight. So I feel like every single conference I go to, there are two subjects of conversation: AI and the fact that everyone is talking about AI, not real things. I'm not going to make that any better today. I'm even going to start with the obligatory what is an agent slide. But I've actually got a point here. I'm not just like rehashing old stuff, although the code on the left, which is the kind of like abstract definition of an agent from Barry Zhang from Anthropic, is definitely rehashed. But the idea is that an agent fundamentally is an LLM calling tools in a loop. And there are kind of two bugs with this code, even though it is 6 lines long and abstract, to say the least. One error, which I'm not talking about so much today, is that the loop goes on forever. And that like hints at a real problem, which is how do you end, when does an agent end? That is not trivial to infer. The other problem is around the tools. And it seems kind of obvious, right? We've got some tools, they feel a bit like Python functions, we're going to give them to the LLM, and it's going to be able to go and call them. And we think of like, we have these 3 tools, and the LLM is aware of their name, so it can call them. But tools are more than just a name. They have a description. Here it's 1 sentence, often it's paragraphs. And they have some schema for the input types. I haven't even included a schema for the output type. But quite quickly, as you add more tools, it starts to get really quite long. So when you look at like real agents with a large number of tools, the amount of context that is being used up by those tools is not insignificant. In fact, Cloudflare talk about if you register all of their API as an MCP server, that uses up 1.1 million tokens, e.g. a bit more than almost any agent can support. And that's before you start doing anything. That's literally just defining your tools. The other problem here, probably easier if I go back to this slide, you don't need to look at the details here, but you can kind of imagine that tools, just like functions, we can take the return value from one tool and we can pass it straight to the next tool. But if we are using the standard mechanism as shown in the code on the left, where we are taking the result from the tool and effectively appending it to the state of our agent and giving that whole thing back to the model and saying try again, then the only way of passing a value from one tool to another is through the context. And that means 1, you're passing all of that data to this LLM provider, which you might not want to do. 2, you're bloating your context with masses of stuff. And 3, you're basically praying that the model is actually going to get the values right. So you have some like BI or data science tool that is taking an enormous amount of data and is ultimately from a SQL query and is now building a chart. Now, if all that data goes through our context, we're basically praying that the model doesn't get a decimal place wrong somewhere and render our chart invalid. And so enter code mode as a panacea that's going to solve all of this. And I think code mode is a like profound step forward. It's also called programmatic tool calling by Anthropic, Codact by Apple, and RLM, recursive language models by the kind of data science-y, sandal-wearing people. Maybe that's you lot, so I won't make that joke. It's all really the same thing. And I think the fact that it has at least 4 different names is kind of representative of the fact that numerous different people have come up with variations on this idea. But the simple idea is you, instead of registering all your tools natively with the agent, you register 1 or 2 tools called run code, and sometimes are like find tools or explore. And now we have this like progressive disclosure where we don't have to give all of the tools to our LLM. It's allowed to go and search for the tools it wants to use, and then it can go and call them either in an individual call or by basically tying together those different calls. And the power is we aren't just the simple kind of programmatic simplistic take the value from one tool and pass it to the next tool. We have full code, so we can go and do composition, we can do branching, we can do looping. We can just go and write arbitrary code to go and make use of this data. Split it up, call two different tools, call tools in parallel, et cetera, et cetera. And of course, the intermediate state, when I call two tools, one with the output from the other, doesn't need to go through the context of the LLM. So we save enormous amounts of tokens that way. And the kind of the promise from Cloudflare, who came up with the code mode term, is 1,000 tools in 1,000 tokens. I think it's even more powerful to talk about 1,000 tool calls with one LLM request, because you can imagine that like now I'm going to go and do this thing. I know it's very programmatic. For example, I'm going to go and create a calendar appointment for every day next year. I don't need to call the create appointment tool 365 times. I write a block of code, which is basically work out the first day of next year, work out the last day of next year. It's very easy, and then call the create tool, create appointment tool 365 times. And this is great until we want to go and run that code. Where are we going to actually execute it? There are lots of different options, and there is a trade-off. We have the tool calling we've already talked about, where we avoid this by not having writing code. We have sandbox services like Daytona, E2B, Modal, and many others. They love this stuff. I mean, Cloudflare is also in this category. They're all telling you that code mode is the answer to everything, because ultimately you're going to pay them quite a lot of money to go and do that. And then you have, and this, I suppose I'm talking here about the general span of like how much control you give an agent rather than just specifically code mode. Then you have coding agents, and on the very far extreme, you have kind of full computer use from an LLM. I am not arguing here that like one point on this spectrum is right and one is wrong. I am purely arguing that there are trade-offs between the different points, that there are strengths and weaknesses, and there are economically and socially valuable things to go and do at numerous different points on the spectrum. And I guess you may be able to guess what I'm going to talk about in a minute from the massive gap I've left on this slide. So the trade-offs, in particular, there is a trend right now from people to say, the more power I give my agent, the cooler I am as a startup, or the more impressive my agent is. So, oh, my agents really need a full VM. I was talking to one of these like sales support AI companies who basically like churn through LinkedIn looking for contacts and then send spam. And they were like, our agents need a full Ubuntu VM. Nothing else will suffice. And that, to me, that is just the like absence of the creativity necessary to work out what they actually want to do. We're just going to give them everything in the kitchen sink and hope for the best. Often that not only is unnecessary, but is actually worse. Yeah, if you have 5 tools to call, you don't need a full Linux sandbox to go and Linux containers to go and run them. Often what looks like a genuinely complex task, like some BI agent, which is what I'm going to show you in a minute, or show you later on, turns out when you simplify it, when you boil it down to what you need to go and do, you've got to like run SQL, you've got to generate chart, you've got to print a table, and you've got all the normal stuff you might want to go and do in your programming language. You don't need the full like expanse of everything that you can do within a Linux container. And of course, the principle here is that if you are the agent, if you are given these 5 tools, it's much more likely that it's going to stay on track doing the right thing than if you give it the full madness of everything within Linux and hope it's going to get it right. The number of different ways it can mess up on the right is obviously far higher. So this is where we get to Monty, our proposal for a solution to this. Monty is a minimal Python interpreter written in Rust, specifically to run code written by AI. It is where it is different from other languages, let's say, is that it is isolated by design. It does not have built into the runtime the access to make any syscalls, to open files, to read environment variables, to do networking, or anything else. You can basically register functions that it is allowed to call, and those are the only functions it gets to call. It is, in its model, not entirely dissimilar to how an LLM works, in the sense that you give it this bunch of tools that it's allowed to call. But ultimately, it is a Python interpreter. It is running Python code, and you can do whatever you like within it. Type safety is massively important in this, because if we can have type safety, and we can have fully typed tools and all of the functions exposed, then we can give the model feedback sooner when it gets it wrong, give it better feedback that means it's less likely to make a mistake, and ultimately increase the probability that it quickly gets to the right result. And so Monty comes with the TY type checker from Astral built in. One regard in which it is can do stuff that CPython cannot do is that we have this support for snapshotting. So I said we operate somewhat like an LLM in the sense of having this list of tools that we can call. The way that we do that is not to take pointers to a list of functions and be able to call them, but instead to basically return to the runtime and say, call this tool for me. And we are able to snapshot the entire interpreter state at that point. So if your tool is going to go and take 10 minutes to run or 10 years to run, you can snapshot the state of your interpreter, go put it in a database, and resume it from that exact point when your function finishes or when you want to resume. Because it has no dependency on CPython, it is just written in Rust. You can call it from anywhere where you can call Rust. So we have a Python SDK to run it from Python, obviously. But we also have a JavaScript SDK. There are third-party SDKs for Go. There was one from Kotlin that was written by Block the day before they sacked everyone, so that hasn't got much more development. And there was one more, I can't remember, maybe Dart. But there will be more SDKs over time. But in principle, this is not tied to CPython. But in general, we'll be using it from Python here. So you can install it with Pydantic Monty, npm command as well. I will be completely blunt here, it is a subset of Python, and it is a very small subset of Python that is enough to let the LLMs do code mode. We are not trying to go and be a true alternative to CPython for you to build your app in. Whether we get to be able to run some subset of applications one day is unknown. But the idea is not, this is an alternative for CPython. There is a graveyard of people who have tried to build CPython alternatives, PyPy being probably the most famous, which I think has now been suspended development. But there's GrailPy, there was IronPython, there was Unladen Swallow. There is a whole range of different Python interpreters. None of them really worked out. And I think the reason is they needed to be 99.109s of identical to CPython for you to be able to move your app across. The day you tried to run PyPy, run your app on PyPy, and one function didn't work, you were like, probably not worth it. We are not trying for that. We're not even trying for 1.9 of compatibility. We're trying to build something specifically for the code mode case. And so, just keeping track of where I am on time, the principle of Monty coming back to this chart of capabilities and versus control is that we fill in this gap where there are not very many other libraries available. Or other tools available. And in particular, setup complexity is one of the underrated things, right? So I can go and use one of these sandboxing services. That's great if I am a well-funded startup. It's not so great if I am an individual who doesn't want to go and spend the money. It's also really problematic if I'm a massive financial institution where I can't just go and plug my credit card into some third-party service and hope the data is going to be safe. I need to go and run my own sandbox. And the complexity of this, where you are doing pip install Pydantic Monty, and now you have the runtime, it works anywhere where you can run in that case, Python, is a massive win. So the advantages, because Monty is running in the same process as the rest of your agent, the startup time, the time to go from I have some code, so I have the result, or the overhead of doing that is around 5 microseconds. That is not a typo, that is 5 microseconds. The snapshot size, if I do want to have this persistence, is, depending on what you're doing, order of magnitude 1 kilobyte instead of about 1 gigabyte if I want to take my full Linux container and snapshot it and go and put it somewhere. And obviously the cost of running it is 0. So this is all very well, but I feel like before I get into more details about how Monty works, it's useful to have a little mini demo of what it can actually do. So I'm going to break out of this for a minute and give you a tiny demo, and then I'll come back. And I know the mic's a bit further away, so I'll shout, but if anyone can't hear me, please shout back. So this is the most simple example of all. We're importing Pydantic Monty. We've written some code. It's just print with an F expression in there. We've got one input, which is the who variable, and then we go run it. If I can run it, I can't run it. And hooray, we get the output. We get hello world printed out. So by default, standard out is connected to standard out on the host, so you don't need to do anything about it. But if you wanted to go and basically have a callback on every print, you could go and do that as well, but here we're just printing straight to standard out. If we go on to a slightly more complex example, still not the full-on let's go build an agent, but demonstrating what we can do here, I talked about this idea that we could have external functions registered. And so I copied this code from PyCon. I apologize, I haven't updated it. Here we go. In this case, we're passing in this function, getWho, which is going to allow us to, and we're going to effectively call that function through Monty. But again, we're not passing a function pointer into Monty and allowing it to call it. Under the hood, what's happening is Monty is suspending execution when it gets to this function and basically returning to the host, call me this function with this input. And so if I run this, we get hello world. And just to prove that I was right here, if I say London in here, OK, we get London Pydata, but you get the idea, right? I'm gonna go back to the presentation. I'm just wondering what order to do this in. And I'm going to talk a bit about how Monty works under the hood. I feel like as we're a Python conference, there is some interest in seeing the internals. Please don't feel you have to get up and walk out at this point. I'm going to talk about the internals of a programming language, but I will come back to some possibly sexy bits of the demo later on. How are we doing on time? We are good. So what does it actually take to go and build a Python interpreter from scratch? There are kind of 5 phases. We pass the code, we resolve a bunch of stuff, we compile that code. I'll explain to you what that means. It's not compiling in the sense of compiling C or C++ or Rust. We go run it, and then we do our weird novel thing about pausing and resuming when we hit external functions. So the parsing bit is kind of the easiest bit of all for us, well, with some massive asterisks next to it. Because rough, the Python linter, has this excellent Python AST parser written in Rust that's used for rough and for TY and actually for Firefly as well. And so you can basically go from code, a bit like what you're seeing on the top right, to this AST. AST is just a fancy word for some kind of big object that represents in code some code. And so we take this AST and now we can go and process it. We don't need to go and figure out, is this an F string and the exact positioning of things? We get back this nice object that has exact positions of every variable that we can go and operate on. I said big asterisk. I'm in the middle of a heated debate, let's say, with Astral, because they think that if you have really long, for example, if you have 1 plus 1 6,000 times, 15,000 times, TY and rough will Stack Overflow and crash. And they think that is a completely credible thing to do, and in their case, it kind of makes sense. In our case, it is less desirable because we care about security enormously, and crashes like that can cause DOS risks. So there is some negotiation going on, let's say, about whether or not we should harden everything inside their AST parser. But with those provisos to one side, this is by far the easiest step in our case. The second step is to resolve names. So obviously our input, all of our variables are just strings. All of our literals are just strings or integers, etc. We need to go and convert them. So we need to go and work out what is local, what is global, when we have functions, what's included within the function closure. And we basically need to go and assign IDs to all of our variables because we don't want to be looking up some dictionary for a variable every time we need to go and access it, for example. And then when we have some unassigned, some unknown thing, like in this case, getWho is not yet defined, we're going to mark that as just some undefined variable and just go and call the host when we see that function. And the host can decide what to do about that. The next stage is to compile the bytecode. So this is the same thing that CPython does effectively. We are not compiling in the sense of compiling it to a binary. If you look at, when you run Python code, you will see there's PyC files next to your Py files. Those are basically Python compiled into bytecode. And so we're effectively going from this nested tree that defines our code into this sequence of instructions on how to run our code. And this is what people refer to as compiling this bytecode. It ends up with effectively a list that looks something like that thing on the right. But ultimately, internally, it's held as basically a list of ints. and each int has a particular meaning. Some of those ints, and when we have very long instructions, those end up being multiple different ints, but this is how the bytecode ultimately work. It's called a bytecode because we're not storing some nice typed list, we're storing just lists of bytes, and then we're going to go and figure out what to do with them once we get them. Then once we've got our bytecode, we can go and run it. And obviously, one of the nice things is those first 3 steps we can do once and reuse if we're running our code multiple times. This we do each time. And so we end up with our bytecode. We're going to iterate through that as effectively a list of things to do. And we're going to, if you look at this expression here, 1 + 1 times hello, well, that will obviously give you hello, hello. What that would look like in bytecode, it would be load a constant, 1, load another constant, 1, perform add on those 2 things, load another constant, hello, into our stack, and then call multiply on those 2 things. So that's some Rust code that goes off and knows how to multiply an int to a string, in this case, just like replicate it. And then lastly, we would call store local, which is going to put the value into our X value that we can then go and reuse later. All of those steps are pretty similar to what would go on inside CPython or any interpreted language. The bit that is weird and different about Monty is how we deal with external functions, because we don't have an implementation inside the language, for example, getenv or open. So if we want to call open or if we want to call our getWho function or anything else, we do it via this suspend and resume process. So you can see that the Monty class at the top there is kind of pseudocode for what the signature of our Monty object. And we basically call start on that, and we either get back the final result if we haven't had any external functions to call, or we're going to get back this tool call object. And if we get a tool call object, then we're going to go and work out what that tool is, figure out how to call it, take the result, and then call resume. And resume's going to give us the same thing, either the done result or the tool call again. We basically iterate over our code like this until we get to the done result, or we get some like resource limit exhausted stop situation. And notably, whenever we get back this tool call, we can choose to go snapshot that if we want, and basically resume from there in future. We care about security enormously. So we have been running the Hack Monty bounty program for about a month now. It is live now. You can go to hackmonty.com and follow the instructions and basically try and find the secret that is within the server by running Monty code. We will pay $10,000 if you find those secrets. Thank you very much to Prefect and Hugging Face, as well as obviously Pydantic for sponsoring that. The first time we ran it with a $5,000 bounty, a security company did find the bounty. They found a very subtle use after free memory bug in Monty and used that to subvert the stack and get access to memory they shouldn't have had access to and read an environment variable. So we fixed all of the issues that came across. We're running a second round of this, and then we're basically going to call Monty. We're going to remove the massive experimental badge once this has been running for a few weeks and no one has found the vulnerability. And there were like, I don't know, not tens of millions, but millions of requests going on all the time. It is slightly terrifying, me having to go and check the list of like submissions to see if anyone has found the secret. So far, no one has. So I'm going to talk about what it looks like to put Monty into production or to put agents into production quickly. Warning, I'm going to do a mini product pitch. I don't know how many people followed the drama of PyCon, but Guido went to the opening keynote, which was basically just a product pitch and was not impressed. So I hope you don't think the whole of my talk has been a product pitch, but there will be 2 or 3 slides that talk about what we do. It seems kind of easy putting my agent into production. I've got an agent, I might have code mode, and I've got some users, I tie them together, and I hope everything's going to work. In reality, that's not what it looks like. We need to add more things in. We need to go and optimize our agent to improve the system prompts. We're going to need cost control because we don't know how much calling these models is going to cost. We're going to need an LLM. That's fine as an individual, but once we're an organization, we probably need some gateway for that. It's not even 6 steps. It's more like 8 steps. We need AI guardrails. We're going to need the audit log, as well as like developer observability. And I guess you could probably have predicted this slide. That's all the stuff we do. So if you're interested in any of those things, come and talk to us. Also, Pydantic Logfire has a very generous free tier with 10 million log spans or metrics for personal accounts. So please sign up for it and play with it. Would love to hear your feedback. And obviously, if you're a massive enterprise, I would like to speak to you even more. Dare I say it? So now I'm gonna go on to a bit more of a long form demo. How much time do I have? Anyone? Okay, excellent. I've got lots of time. I don't know whether I'm going to need the full 20 minutes, but I'll walk through an example. So I've talked about code mode lots in regard to agents. I want to start by showing what that looks like in a relatively self-contained example. The forfeit here is that the agent is not complicated enough to actually need code mode. So I'm going to show you what it does, but it's probably it would probably use slightly more tokens in this case than not using code mode. You will see when I get to a more complex example why I need it. So here we have this weather agent. We give it some instructions. We define what model we're going to use. We register some tools with it. This getLatLong tool, and this getWeather tool, and convert temperature. And we say, what's the weather like in Paris, Tokyo, in Paris and Tokyo? We've obviously got like dummy answers for now. But critically, we have this one line here, this capability on the Pydantic AI agent, which basically converts all of those tools into being used as code mode rather than being registered directly with the model, which I'll show you what that looks like. It's important to say there is nothing in Monty that means you would have to use it with Pydantic AI. As you can imagine, our agent framework has better support for it than others. Although I did see there's a bunch of people who, for some reason, are still using LangChain who want Monty support. So I guess it will come to other agent frameworks at some point. But if I go and run this example, what was it called? It's called Agent Weather. You will see some dirty gray error because I haven't set things up properly. It runs and it completes. But probably more interesting, if I open that in Logfire, you should be able to see, and I apologize for that this is going to be slightly hard to see on screen, but you can see without even going in and looking at the details of the agent run that there's fundamentally two calls to the LLM, one at the beginning and one at the end. And in between, if we look at I'm trying to make this big for you. We can see the actual exchange with the LLM. So we can see the system input, the user input, and then we can see the code that the LLM chose to write to go and basically take the output from one tool, pass it to the next one, pass it to the next one, and then return the ultimate result. It got back a bunch of data. It thought for a bit and turned that into a one-sentence explanation. The other interesting thing to see, if you look at the span for the actual agent run itself, you can see the schema for the tool that was registered. And you see here we have a bunch of explanation about why the rules for the LLM of running Monty code. And then we have the typed signatures of the different functions that it is able to call. This is how it's able to figure out how to call them in a type-safe way. And then the full schema is basically just the code to run. I'll run that one more time with code mode switched off. I don't know whether it's going to perform better or worse in this case, but something will happen. And you can see it running here in Logfire. And you can see immediately that it's taken 5.2 seconds instead of 2.7. And if we look inside what's happened, you can see that's because we've had 4 different calls to the LLM instead of 2, because it's had to take the results from the first tool, pass them to the second tool via the LLM context. In this case, as I said, because it's a very, very simple example, we actually used 1.5K tokens the first time and 1.3K tokens the second time. You will see, I think, in a minute when we get to more complex examples where basically either it will be enormously slower or it wouldn't even be feasible to run these examples without something like code mode. So I'm going to go on to a more complex example. I'm trying to make the font as big as possible to help people, but if you can't see things, please shout. I'm happy to try and make it easier. I'll do that, and hopefully that's big enough for you to see. So this agent is doing some e-commerce analysis. So we have a bunch of different tools registered. I won't go through how they operate, but basically it can go and run SQL queries, and it can list stuff about the database that it has access to work out what's going on. And ultimately, when we come to run our agent, it's as simple as asking some question about our big e-commerce data set. And so if I go and run that example without going through in much more detail, you should see this should be a longer run. I suspect if you disabled code mode and tried to run this example, it would just run out of context or die pretty quickly. This will take a number of steps, but we should be able to look at what's going on while it's running. And you can see here, I guess, the system prompt, and then it's going and running some queries to investigate what the schema of the database is, looking at the schema of particular tables. Once it's figured out that stuff, it's able to then go and query these attributes, and it thinks for a bit, and ultimately it returns some results, answering our question that you probably don't care about, so I won't go into it in detail. What you notice, though, when we do this is that an awful lot of the time is actually spent figuring out the schema of the database before we go and run. And so the obvious way to solve that, I'm actually going to show you this in Logfire, is by having a prompt which where we effectively include the schema in the system prompt, and then it can basically avoid those steps. This works way better in examples like this because it doesn't need to go and do the exploration phase early on. But what happens is if you then have any mistake in your schema, it takes way longer because it actually has to, thinks one schema is going to happen, it gets back a bunch of errors, and it has to go and retry. And so that's where Logfire's optimization functionality really kicks in, because if you look, that is not what I want to look at all. I'm going to basically cut to the chase and do a, this is one I made earlier. But if we look here, you'll see, so let's look at the token count from wrong tab. Look at the token count from those. Actually, it was a different question. But what you can see here is that basically I ran this with a version of the schema, and you can see it consumed 35, 41, and 16,000 tokens respectively, running 3 different cases, because it basically had some mistakes in the schema. And once I was able to fix that schema by basically using the optimization function in Logfire, here, where I can basically go and autonomously improve the system prompt, I'm able to basically get way lower cost of running these things. So if I go back to that very quickly, you will see that the optimization was able to cut the token count from 35 to 8, 44 to 17, and then the last case was similar, actually slightly worse. But you can see the kinds of changes that the optimization was able to make. If I look here and I do compare, you can see that basically the agent is able to go and optimize the system prompt completely autonomously, because it's able to immediately see from the traces themselves the mistakes that it was making. So I think we should have some time for some questions. I'm looking for what I'm talking about. Thank you very much. All of my code is up on that link. Thank you very much. Yeah, there's some questions here. I don't know if there's a microphone or if you just talk. Just talk and we'll. Yeah. So Pydantic graph, we have graph support because we want an alternative for people who are frustrated by LangGraph. I think graphs are fundamentally a mistake. I think that the true graph is code, and if you want to give real autonomy to the agent, you should let it write code. And so I think ultimately this code mode stuff. There was an article from Tarek at Anthropic the other day, basically saying that Claude Code itself is going to have the capacity to run workflows, where it's basically writing code to do some more complex steps. That is, I think Harrison just got himself confused when he thought graphs were good for AI. and then they spent 3 years telling everyone it's important because they couldn't make a second mistake. I think it's completely clear that graphs don't help anyone in this situation. They're a terrible primitive for durable execution. You should use a durable execution platform. I think code mode solves the things that went out to solve way better. But I can talk to you more about our graph or anyone else's afterwards. The second question was about seatbelt and bubble wrap. They are OS level isolation. They are a good option in some situations. They take enormous amounts of configuration. They're very, very brittle to the particular architecture, operating system, version that you're running. So if you are a massive financial institution I won't name who want to go and run code mode across enormous fleets of different machines, and you have to go and configure every single one to be absolutely sure that it's right, and if you get bubble wrap slightly wrongly configured, now it can break out and do anything, that is quite terrifying. Monty starts from a completely new piece of technology and is like, we try and add features, and if we get something wrong, it will almost certainly just crash. There's a chance that like you give excess access by making a mistake is very small. Question there?
Get the microphone to you.
Thank you for the talk. I was wondering if you have any thoughts you can share about how to make those tool calls connected with each other through some serialization, glue through some, communication protocol. There's this nice library called Pydantic. You might have heard of it, that has base models, right?
Yep.
Any plans for it, and also any plans for pandas data frame, structured data?
So on the second point, there was this enormous PR. I think it was about 20,000 plus. It's now 30,000 plus, where someone added NumPy support and basic pandas support to Monty, and I was about to go and like tell the guy what an idiot he was and how we ever going to accept this, and then one of my team pointed out he was a senior engineer at a massive hedge fund who were about to be our customer. So I backed off, and I said, that's really interesting. I don't think we can add pandas because there are multiple different alternatives, polars and pandas. There's lots of file system and networking access, subtlety. NumPy is much simpler in some ways because it doesn't do any of those things, and there are not many like alternatives to NumPy. And so we could possibly add a like subset of NumPy. He then went and did the work to make NumPy work, and now I've got this like 25,000 line PR to review, and I'm like, we've got a lot going on. You can basically, I'll go very quickly and show you how this case is doing SQL. If you look here, our query function, the like query function it has access to is entirely implemented on the host. And that is the best way to do all of these things. Whether you're doing data frame stuff, whether you're doing SQL, whatever you're doing, you go and do that really complex stuff on the host, then you just expose the function in, and I think that would be the way to do a pandas type thing. We have to do a bit of work on class support inside Monty to make that stuff easy to do, which is sort of an answer to your first thing. I think, do we want to have some kind of validation inside Monty? I'm not falling over myself to implement Pydantic all over again from scratch, but that may end up happening in some form. There's a question here.
Yeah, thank you very much. Really good presentation. Excuse my naivety here. So you got Monty and then you got Logfire. Could you just briefly explain how Logfire complements Monty? Yeah, that wasn't very clear.
You sound like lots of VCs I speak to who are like, why are you doing this other random open source project? The true answer is that I could see where this was going. I could see that like Monty is the answer everyone needed, and I just couldn't resist going and building it. We have a rule inside Pydantic that I'm not allowed to write code that goes into production on the main system. So when I'm busy, not everyone waits. And so I basically got distracted and built Monty. And we now have lots of open conversations going on with Anthropic, with OpenAI, with companies like Netflix to go and use it. I know that Hugging Face is already using it in production, a bunch of other companies. So there is a possibility that we might have some more like concrete links between Logfire and Monty, but ultimately the best answer I can give is we have a whole bunch of tools that form this stack for letting you build with AI. Some are open source, some are not. Was there another question? Don't ask it. Please, no questions about my business plan.
No way. There won't be about that. The first one is quite simple. You said that this Monty state is snapshotable. How is it represented and how does it work? And then the second one, since you and also sorry, like an apostrophe to the last one, and why is it so small compared to other states? And then the follow-up, since you mentioned the Monty and the fact that you were talking to other providers, the first thing that I thought as I saw the logs coming through in Logfire was that having like the LLM write code is super easy to read, and it's much more intuitive than see this whole blob of JSON of tool calls. But then I immediately thought, like, if I use Monty on some other platform, like say Langfuse or whatever, what will I see? And then immediately was like, what kind of efforts are?
I'm being told I have to wrap up, so I'll answer those questions really quickly, and I can talk to you more afterwards. First question was, how do we do the snapshotting? Basically, we just go and wrap every single Rust struct with serialized and deserialized from SERDI, and then we serialize it in this particular case with bin code, but it could be to JSON, it could be to anything. It's basically some representation of the internal state of the Rust library. It's small because it's just the runtime. If you go and create a like 1 GB string, you're like, now we have memory limits and stuff like that, but then your output would be 1 GB. But the point is, we're not like snapshotting an entire virtual machine or like Linux VM as we would be in most snapshotting. What you would see would be basically a pile of JSON in other platforms, including some strings. So we do a good job of making that pretty and easy to read. In answer to the previous question, that is obviously not sufficiently of a defense, as in if Monty really takes off, our competitors will also show the code stuff. I think without talking about it in too much detail, there are some other things we can do that may be more defensible in linking Monty to Logfire. Thank you very much.